I work for Red Hat. I'm an engineer at Red Hat. Has anyone heard of Red Hat here? Does anyone know who Red Hat is? Nobody? Okay, a few hands, right? Well, if you don't, we do have a booth outside. Go and say hello to the guys out there. They'll tell you all about Red Hat. For those of you who do know about Red Hat, you probably know that Red Hat's pretty famous for Linux. It's pretty famous for Linux. It's pretty famous for open source. How does this all play into middleware and well, big data? Well, it's a little secret. Red Hat's not just Linux. Yes, that's how we started out over a decade ago. We do a lot more than just Linux today, including middleware, storage, big data, etc., etc. So, like I said, go speak to the guys outside. They'll fill you in a lot more on what Red Hat is. The only common thread that there is across all of these different parts of Red Hat is open source. Now, who's familiar with open source? Or rather, who's not familiar with open source? Okay, good. I'm glad everyone knows what open source is, because I'm not going to sit and explain what that is at this point. I don't quite have the time to do that. I'm going to talk about what Red Hat's doing in NoSQL specifically, right? A little bit about me. I'm the platform architect on a number of Red Hat's enterprise products, specifically the data grid, and also in a lot of Red Hat's upcoming NoSQL and big data research. I kind of head a lot of that. In addition to that, I'm the founder of Infinispan, which is an open source data grid project. That's kind of my background. That's why I got into Red Hat in the first place. I work on a number of specifications and expert groups in standardizing data grids and the way data grids are used and accessed. My blog and Twitter feed are there if anyone cares to listen to my blatherings online. So jumping right into things, I'm here to talk about NoSQL, right? Now, the way I look at things, right, I think of NoSQL as an evolution of data, the way data is stored. Everyone's familiar with relational databases, right? Everyone's familiar with simple file system-based storage. And this is stuff that we kind of grew up with. This is what we were taught at universities and so on and so forth. This is where we built most of our applications. And today, everyone's talking about alternate forms of storage. Why? What's the big deal here? Why are we changing something that we're so used to that actually works quite well for the most of us, for the most part? Well, let's have a look at that. So not too long ago, right, once upon a time, disk space was very, very scarce. It was expensive. You couldn't really get a lot of storage space on your servers, even on your desktop computers. It was expensive to even get a few megabytes of space not very long ago. Now, this has changed very quickly, very, very fast, but once upon a time, like I said, it was scarce, it was hard to come by, and as a result, this is where the relational model came about. Now, the relational model is very strongly backed by set theory, it's very academic, it's a very powerful mechanism of storing data, of organizing data and storing it. Who's heard of Codd's normal forms? A few hands? Okay, good. Who actually uses it today? Very few, a few, even fewer, right? The reason why, right, is that the relational model, everyone thinks it was designed for consistency, and yes, it was. Everyone thinks it was designed for a structured way of organizing your data. The biggest driver behind the relational model was, quite simply, efficiency in storage, because disks were expensive. You couldn't actually denormalize your data and store lots of copies of it everywhere because it was expensive to do. And this is why the relational model and Codd's normal forms came about, to try and store this data very, very efficiently on disk, to minimize the amount of space you take on disk and save cost as a result. Now, the world's changed a little bit from those days. First thing is, disks aren't that expensive anymore. They're actually kind of cheap. You can get lots of disk space today without really thinking very hard about it. Memory is cheap as well. You don't necessarily have to store everything on disk. You can store your entire database in memory a lot faster, a lot quicker, right? And the other thing is networks. So networks have become faster as well, more reliable, more available, and as a result, you can now store data across multiple servers connected via networks in a very reliable and efficient way and get a lot of capacity. So suddenly, you think about all that stuff that we did with the relational model, with Codd's normal forms and things like that. The main driver behind that, to save space, doesn't actually apply anymore. You got lots of space. Space is cheap. You can get space. Other things become more important now. Now, because your data is distributed across multiple servers, Suddenly high availability becomes more important. The ability to have data striped across multiple servers, to scale outwards, scale horizontally, to grow with data volumes and transaction volumes, that is more important than trying to save space, right? In addition to that, in addition to high availability, fault tolerance becomes important as well, fault tolerance and scalability. This is partly driven by cloud. Now, cloud suddenly makes it very easy to provision new servers on demand, to grow elastically, to react to consumer demand and things like that, which suddenly means that your data storage system has to be able to do that as well, has to be able to cope with that. And relational structures don't do that very well, all right? Remember that the relational model was originally designed to run on a single machine, on a single server. Whatever you see today that most database vendors do to try and cluster databases, to try and distribute databases, they're sort of hacks on top of a model that was designed to run on a single machine, right? And the other big thing, of course, is the relational model. We never really liked it anyway. I mean, it doesn't really fit well with object-oriented programming. It does not really fit with the development model that most developers use to build business software. And there are always layers in between, like tools like Hibernate and object relational mappers and stuff like that, which are all additional layers and hacks to make a relational model work with the software that we write. So this is kind of where NoSQL comes in. We have a chance to reinvent the way we store data and rethink things, which is actually a really great time for us right now. It's an important part. The first thing that we get with NoSQL is horizontal scalability on commodity hardware. We're not talking about big, expensive, specialized servers, which cost a lot of money and very hard to maintain. We're talking cheap commodity servers that you can buy off the shelf. You can plug a lot of them together, build a big grid, a big network out of them, get a lot of capacity. If servers fail, as they do, you throw them away, put a new one in. Your service is generally uninterrupted. Your service is elastic and scalable, and this becomes a very interesting data storage mechanism. In addition to horizontal scalability, we also have high availability in NoSQL. The reason why we have that is, well, provided we're talking about a distributed NoSQL engine, there are many different types, which I'll talk about in a bit. In a distributed NoSQL engine, your data is inherently spread across multiple servers. So if servers fail, like I said, your service is uninterrupted. Your service is highly available. And the third part is a flexible schema. You're no more, this is another reason why NoSQL has become popular. People don't actually understand what data they have or what they want to do with their data. They just know that they have a lot of it and they want to capture it. And they'll figure out what they want to do with it later. Now, this does not really work with the relational model again, because the relational model kind of forces you up front to think about the shape of your data. It asks you to structure your data in a particular way before you can store it. NoSQL kind of takes that the other way around, saying store it first and you can structure it later. You can figure out what to do with it later. And this is where the soft schema features of NoSQL come in, and that's why it's quite popular. Now, one of the things with a lot of NoSQL engines is consistency. And this has it's been pretty highly publicized. It's one of the big concerns that a lot of people have with NoSQL, saying relational databases give us strong consistency. We are strongly consistent. We know exactly what's happening in the database. A lot of distributed NoSQL engines are not strongly consistent. They are what we call eventually consistent. And the world has a hard problem swallowing that, dealing with this. How do we deal with this eventually consistent thing? Well, firstly, it's actually not that hard to deal with. Who's familiar with Eric Brewer's CAP theorem? It's kind of academic. I'm not going to go into it in too much detail, but it was a CAP theorem that actually defined what consistency is. And to sum it all up, the CAP theorem basically suggests that if you want to have a highly available, highly distributed system that can be elastic and grows with size and demand, it can't be strongly consistent. There's no way it can be strongly consistent, right? That's basically what Eric Brewer's theorem proves. What it does suggest is that your consistency will always be weak or eventual in such an elastic system. Now, that's actually not so scary, because if you look around us, there are lots of very big distributed systems that are eventually consistent and that work really well. The biggest example is the internet. Right? It kind of works, right? What do we think? Do you think the internet works or not? right? I think it kind of works, right? And it is eventually consistent. There is no strong consistency model around the internet that maps domain names to IP addresses and so on and so forth. It's all eventually consistent, and it's the biggest distributed system in the world, right? Now, a lot of smaller distributed systems can work just as well, as long as we think about our data model, we think about our application, and we build our application to deal with eventual consistency. The problem that a lot of people have today with eventual consistency is that they're used to building applications for strong consistency, for a relational database, and then they try and move that application onto an eventually consistent data store and then wonder what's going on, right? I mean, yes, it does involve a little bit of re-education, a little bit of rethinking, but we're at the stage where we can now do that to gain all the benefits of NoSQL. So what I want to talk about for the rest of this talk really is to talk about the different NoSQL engines out there. NoSQL is a very, very young space, right? It's a very young, very nascent space. The terms are very ill-defined. I mean, just the very term NoSQL, what does that actually mean? Not SQL? What does that mean? A chair? A chair is NoSQL, right? But anyway, there are a couple of different broad categories out there of storage engines, and I want to talk a little bit about that. The first one is a relational database. We are used to relational databases. We know what these are. I'm not going to talk about this too much. The next thing is key value stores and data grids. Now, this is a particular type of NoSQL engine out there. Data grids tend to be in memory. They tend to be distributed across multiple nodes to give you very, very fast access. It stores data in key value pairs, a very simple data structure that gives you a lot of power in terms of scalability and performance. Because the data structure is simple, most key value stores can be screaming fast, can scale out very, very easily, but the trade-off is your data structure has got to be simple. A lot of the key value stores out there today, all of these out there are basically, they're all open source projects that I've mentioned. I tend to focus on open source. They all tend to be based around the Amazon Dynamo paper. Who's heard of Amazon Dynamo? It's not a product, you can't buy it, especially on Amazon. What it is it's a white paper. It's actually an academic paper that Amazon wrote with certain designs and ideas on distributed computing. And a lot of these projects that I've listed up here are all based on the Amazon Dynamo concept and the idea. The next one I want to talk about, document-oriented stores. Slightly different from key value stores. Very similar in that they map keys to values, but the values aren't simple values, they're documents. They're documents specifically, they're either XML documents or JSON documents, and the big benefit you get from a document-oriented store over a key value store is that your data structure is slightly more complex, and you can concurrently update different parts of that document in real time. So you get some very interesting effects over there. And in addition to that, document-oriented stores also allow a certain amount of schema enforcement. You can actually add validation rules on top of that, saying that these parts of the document that are valid, these parts that are invalid, and so on and so forth. Graph-oriented databases, this is a bit of a niche, but it is a very interesting niche because it solves a specific problem really, really well. I actually know the CEO of Neo4j. He's a buddy of mine, and he always talks about every data model in the world being a graph. I actually don't believe that, but that's what he says. Essentially what it is if your data model is structured in a way that every piece of data is related to another piece of data, forming a graph, and you want to navigate that graph, and that's your primary pattern of data access, is navigating a graph, graph-oriented databases work really well for that. It's extremely fast to navigate such a graph. A good example is Facebook. I mean, the social graph, the social network that you have is actually a graph of yourself and your friends and your photographs and whatever, and they're all related, and you can navigate that graph very, very quickly using a graph-oriented database like Neo4j. Column-oriented databases, these things have been very, very popular for that big word up there, big data specifically. Column-oriented databases tend to scale volume very, very well. First popularized by Google. Google essentially wrote the big table paper. They invented an internal technology that they use to store large amounts of data. Hadoop effectively became a clone, an open source clone of Google's big table. and Cassandra then grew from that. So there are a couple of projects out there that are column-oriented. Column-oriented is very good. Think of column-oriented as a key value store with an additional dimension. Very highly optimized to deal with massive data sets, very highly optimized for very fast writes, for quick data capture. And it scales to handle very large volumes, often on disk rather than memory. So the big difference between key value stores and column-oriented databases, again, is key value stores tend to focus on fast data as opposed to big data. Well, this is more big data than fast data. So how are we doing so far? Have I sufficiently confused everybody in the different areas of NoSQL? Okay, good. So what does Red Hat actually do in this space, right? Now, like I said, Red Hat is primarily an open source company. A lot of the projects you see up there, they're all open source projects. They're all free, usually LGPL or Apache licensed or something of the sort. I'm just going to give you a brief overview of what all this is and how it all kind of plays together. So who's heard of Hibernate? Yeah, very, very popular library, isn't it? Everybody uses it. So I mentioned earlier that there's a big mismatch between the relational model and object-oriented programming. Hibernate tries to solve that problem for you. Hibernate acts as a mapping layer between your object-oriented programming model and relational data structures for a relational database. So it decouples that. So this means that when you're writing code, when you're building an application, you don't need to think about databases, you don't need to think about relational structures and forcing your data to fit this shape. No, all that happens automatically for you. Hibernate does that for you. You just think in terms of Java objects or whatever programming language you're using. So that's the Hibernate ORM side of things. ORM stands for Object Relational Mapping. The next interesting technology on the relational side of things up there is TID. Now, it's probably something nobody's ever heard of. I can barely pronounce it myself. So it's an interesting project that what it is data aggregation or data virtualization, if you will. Very, very cool concept. What TID does is it sits in front of your database, well, specifically in front of multiple databases, and makes it look like one database to your application. So most people write an application, they're used to talking to a database or a data store. The moment you got to talk to multiple data stores, that makes your application kind of complex, isn't it? Oh, I'm looking for this piece of data. Is it in database A or database B or database C? God, that's confusing. And that adds a lot of complexity to your application. TID gives you the power to just say, I just need this data. You go find it, wherever the hell it is. And TID acts as a broker in between different databases. It's also very useful because you can then do a lot of things with your data. You can split up your databases, you can fragment them, merge them back together again, change the shape of the way you're storing stuff. Your application doesn't need to know about it or change or do anything. The application just runs. It's just asking TID for data. It's essentially data virtualization, as I said. Now, one of the interesting things that we're doing with TID at the moment, right now, TID is pretty much relational. It works with different relational databases. You can have half your data in Oracle, half in Postgres, half in MySQL, and your application doesn't need to know about it. But we are changing, or we are enhancing TID to also work with NoSQL. So, for example, you could have half of your database in Oracle and the other half in Hadoop, and something else in Infinispan. And your application, again, does not need to know or care about it. All it knows is, I'm asking this virtual data service for data. Right? So very, very interesting from an application developer's perspective. Makes maintenance very easy, makes migration of software very easy, all sorts of cool things there. Let's look at the non-relational side now. This bubble over here. The top thing you see there is Hibernate Ogm. Now that's a project that I actually kicked off. I started that some years ago. OGM stands for Object to Grid Mapping. So just like ORM, which is Object to Relational Mapping, which maps Java objects to relational databases, OGM maps Java objects to data grids. Quite simple. Or actually any key value store or any NoSQL store. That's really what it does. Now this is extremely powerful because unlike relational databases, there is no standard in NoSQL, right? At least in relational databases, you've got standards. You've got SQL 92, you've got, certain standards that most database vendors more or less stick to. In NoSQL, there is no standard. It's the Wild West, right? Anything goes. So to try and migrate an application from Hadoop to Cassandra and from Cassandra to Infinispan or whatever, it's a nightmare for most people, right? It's really, really complex to do. But with Hibernate OGM, that becomes easy because all that complexity is then absorbed by Hibernate OGM. Just like you use Hibernate with a relational database, you would use Hibernate OGM with a NoSQL database. Right? You think about Java objects. You don't need to think about column stores, key value stores, converting that to a JSON document to put it in MongoDB or whatever. Right? All of that is hidden from you, and it makes it very, very easy to develop applications. Now, my holy grail around that is to actually build it to the point that you can migrate an application that's using Hibernate ORM on Postgres, for example, onto Hibernate OGM using MongoDB. Wouldn't that be cool, right? So yeah, that's what we're doing in the non-relational side with Hibernate OGM. Infinispan, I've already mentioned, it's a data grid. It's an in-memory key value data grid. Very, very fast access to data. ModeShape is again, it's a document store as well. It's a little bit like MongoDB in some ways. And then you look at the things in the middle there, the intersection. We've got transactions, of course. Now, we've always had a very, very strong history, a strong backing in transactions. So we do have a transaction engine that overlaps all of this. So even for non-transactional data stores, we can actually apply a two-phase style transactional guarantee over it, which is very important for applications. Hibernate Search, that's another very interesting project that we've created. It basically allows you to do full text style querying over your data model. So imagine if you could have a Google style text box to search over all of your data in your database. How cool would that be, right? Using full text queries, using likes, using synonyms, typing in your spelling errors as well, and it still finds the stuff you're looking for. That's what Hibernate Search does. It's basically Google for your database. Right? Very, very powerful stuff. A lot of websites use it. So very often when you look at a website and you just see a search box which just says search for everything on this website, it's like, wow, how does that work? I mean, I'm searching over my contact list. I'm searching over my history of transactions. I'm searching over everything in one go, in one text box. Yeah, that's probably using Hibernate Search. That's basically how it works. The little bit in the middle, CDI. Oh, actually, let me go through content storage first. So relational and non-relational are all data storage. It's all storage of data for your application. Content storage is more about storing files that you'd serve up in a web app. For example, a content CDN, whether it's images, movies, video clips, being able to serve up stuff like that. So Red Hat's got a couple of solutions around that as well. Again, it's all open source. JClouds and S3 basically give you the APIs to store things on a cloud, whether it's on Amazon or Rackspace or Red Hat's cloud. GlusterFS is a very, very interesting technology that sits underneath all of that. Gluster is a distributed file system. Think about it as very large-scale NFS that actually works. All right. Who's used NFS here? Who's annoyed by NFS? Everybody, yeah. NFS is kind of good. It's the de facto standard, but there are lots of problems with it. And Gluster basically fixes those. It gives you a proper, highly scalable, distributed file system, which can address terabytes and petabytes of data. And again, very good for building out a cloud service, for example. If you want to build something like S3, a good idea would be to start with Gluster and then build the APIs on top of that. The little thing in the middle, CDI. CDI is something that encompasses all of this. CDI is a programming model, right? Who here, any Java developers in the room? Anyone who actually writes Java code? Okay, CDI is quite Java specific, so I'm not going to go into it in too much detail, but it basically is a high-level API for Java. It's a standard. It's a part of Sun, now Oracle's Java EE standard, to make it very easy to access any of those data tools via your application. So yeah. So all of that is where we are today with Red Hat. Now that's of course not everything. I'm doing a lot of stuff right now in NoSQL and big data for Red Hat. One of the things we're looking at, better integration with existing NoSQL engines. So specifically Hadoop, Cassandra for storage, things like Lucene for search, for indexing, lots of analytical tools out there. I mean, storing a lot of data is pretty useless if you don't have the tools to actually search through it, to actually query it, to actually do things with that data, right? Especially if they are opaque blobs that you're storing that are unstructured and you don't even know what's in it. So having the right tooling is critical. So enterprise-grade tooling, that's one thing we're looking at, including monitoring and management. This is one of the big issues with things like Hadoop and Cassandra. You've got to deploy it in hundreds of nodes or thousands of nodes. How the hell do you manage all this? It's really hard to do, and there's very little proper tooling out there to do that. So again, these are areas that Red Hat's always been strong with in managing lots of Linux servers. So again, we're applying all of that to big data engines as well. Data mining and querying, as I said, big data is useless without it. But what I think is most interesting right now is the last bit over there, stream and complex event processing. So having lots of data is, again, well and good. You're capturing lots of data very fast, again, well and good. You're storing it, you can do that. But you want to be able to react to that quickly. You want to be able to understand something's happening now, I need to do something about it, right? And again, these are things that Red Hat does really well. We've got rules engines, we've got intelligent systems. It's tying all this up together, stream processing engines, to be able to deal with changes in the data stream that's coming in and do something about it. Whether it's something simple, like alerting a sysadmin saying, oh, I think that server's getting overloaded, you got to do something about it, or something much more complex, like, oh, I think there's, I can detect by this pattern that there might be some fraud going on in this particular transaction, go kill it and shut it down. You can do lots of cool things there. So that's kind of where we're going. Now, we need to do this. We do live in an era of big data. We live in an era of big data, like I said, generated by machines, mobile devices that are always on, everyone's always connected, and it's producing a lot of data, right? Now, we need NoSQL to store this data. We need the tools to analyze this data. I'd even go as far to say as we need the machine intelligence, as I said, to react to this data in real time, as I've mentioned. Before even human intervention can come in. I'm pretty much going to leave you with a couple of facts here as food for thought. That's always fun statistics there. And with that, I'm going to wish you guys a very good and enjoyable conference, and hope you learn lots. And if you have any questions for me, I am going to be around for the next couple of hours. I think I've got a couple of minutes for questions if anyone would like to. Any questions? Okay, well...
I've got one.
Oh, you do? Okay, cool. Why not?
How do you handle data quality across that type of grid?
That depends. Now, when you talk about quality, are you referring to validation of scrubbing invalid data?
Finding it, scrubbing it, identifying duplicates, inappropriate data,
Yeah.
Reacting and visibly reacting to something that's not of the customer concern.
What I've seen people do, right, in the case of the data grid at least, is very different solutions. It depends on what you're deploying the data grid for. Now, if your primary purpose to use the data grid is speed, then you want to have that scrubbing to happen offline. You do not want to do that in real time. We're talking of being able to write to the grid or store data in tens of milliseconds. So you're storing data very, very fast. You can't stop and validate data at that point. So you would then have an offline process that scrubs things. You can do that by putting things on a queue. That's been very popular. What I've also seen is people try and do it online as well, which again obviously slows things down a lot, but that's the trade-off that you have. The reason why we don't actually have any of this built into the data grid is purely because we don't want to hold people up. We don't want to force people into a particular way of working. So if you look at a relational database, you're almost forced to do that validation and that structured check at the time of writing data, which means that even if you don't need it, you're paying the cost of that.
Great, thank you. Anything else? Yeah.
Yep.
We got a microphone anywhere?
Alex Tau Arate. Just on Gluster, you mentioned it as a public cloud, in a public cloud context. I mean, do you see it also as the way that private clouds are going to go from a storage perspective?
Oh, absolutely.
And do you just see it completely as being a completely different way of trying to do storage in a private cloud as opposed to more efficient SAN and NAS?
Absolutely. I mean, that's the biggest use case I've seen for Gluster, actually. It's not so much public cloud, but private cloud. Gluster comes with a lot of very interesting tools, including a REST API that is compatible with Amazon S3. That you get that out of the box. So if you install a bunch of Gluster nodes, not only do you have a very big, effective NFS partition, but you also have it exposed via a REST API, which is compatible with S3 and Rackspace and a few other things, I believe. So yes, it's a very, very interesting solution for building private cloud storage.
Thanks.
Wonderful.